on the spectroscopy portion. This is going to be mass spectroscopy, spectrometry, excuse me, first. And then we're going to get into the ones that are more light-based. And then we're going to electromagnetic radiation, actually. And then we're going to get into nuclear. Now, organic chemists really like their mass spectrometry, and they really, really like their NMR. That's their favorite ones. That's nuclear magnetic resonance. And basically, that's very similar. Actually, it's the same technique, just applied slightly different as an MRI. Okay? So that's actually what an MRI is. In the case of an MRI, you just monitor like one or two or few peaks and map it out. Whereas NMR, you're going to actually see all the peaks and you won't need to spatially map them. Okay. And so that's the big difference between those. Mass spectrometry, it is used incredibly heavily in the biological fields, but you don't normally actually interact with it as a medical professional unless you actually go in the labs. Okay. And so it is something that kind of gets ignored. In fact, some of the best breakthroughs, the biggest breakthroughs over the last like 5 years, has been because they basically do this mass spectrometry 4 times back to back. Okay, it's called a quad pole. Okay. And so this is going to be labeled in this book as structural determination because that in organic chemistry, they don't really care about like fundamentals of how the universe works. They just don't care, right? It's an applied science. It's very focused on making stuff, right? And then characterizing it. Did I make it right? Okay. And so keep in mind, I'm going to talk about these. I'm barely going to brush the surface of these fields. And I'm really only give you enough that like you understand how they work to some degree. And you can read a spectra. Okay. This is not even close to everything about these fields that you can learn. And I could teach an entire class about basically every single one of these techniques. In fact, I could probably teach an entire degree about vibrational spectroscopy. Having said that, I am like world class level of knowledge and credentials in vibrational spectroscopy, which is the infrared that we'll do in Raman and a few others. So I'll take the longest on that. I know way too much, and you might want to try to get everything you can from me on that, because my advisor was like one of the top 100 spectrometrists of the, well, spectroscopy. He would have killed me if I called him a spectrometrist. Spectroscopists in the world. There's a slight difference between spectroscopists and spectrometrists. Spectrometry is measuring, just the measuring. Yeah, the other is designing, observing, calculating, analyzing everything. So it's the broad field. Yeah. He made new instruments. He pioneered entirely new methodologies, like 10 different ones. Yeah, he would have. I said that once in front of him that I'm a spectrometrist. It's like you never. He literally smacked me and said, "You never fucking call yourself that again." Swore me up for like 15 minutes. You don't just measure shit. He was quite a character. You'll be spectrometrist at the end. You'll have some degree of understanding of how to measure. No, spectrometrist is the act of taking the samples. They prep the samples. They use the instruments. They measure it. A spectroscopist can design new instruments. They understand the theory behind it. They understand how it works. They understand. No, you're not going to get. That's way too much time. Exactly. So mass spectrometry is going to provide insight into the mass of the molecule, and we're going to fragment that molecule typically before we go ahead and process this, okay? Now, mass spectrometry is actually a portion of many, many, many instruments. Okay. Have you ever heard of things like GCMS, IRMS, any of those sort of stuff? Okay, so if you've heard of those before, what those are is the MS is the mass spectrometer. And very often you have another thing that you put in front of that to go ahead and either fragment it or separate them or do something. Okay? Because just knowing the mass of some, like the whole molecule, while helpful, is not as helpful as it can be, right? But fragmenting it, then separating those fragments, then learning the mass of them, that's actually extremely helpful, right? So again, this is going to be fragmenting the sample typically, and you are going to measure those different masses for this. It's actually going to measure the mass over charge. Okay, that's the actual relationship you're going to measure. And so this is overall how a MS works. Again, this is like a simplified MS. You can make these more complex. You can stack these up. You can do lots of things, right? But this is overall will give you the gist of any instrument. Okay, all of them are going to work something like this. Okay, so you're going to have a sample source, right? This could be suspended in a gas. It could be a lot of different things. Okay, but you have a sample source. What you're going to do then is you're going to take that sample and you're going to get it into a vapor phase. Okay, because you need the molecules to be separated. Okay, not interacting so much with each other. Then what you're going to do here is you're going to put it between two accelerating plates. One is going to be positive, one will be negative. Okay, you can actually flip these depending on what you want to look at. Typically, though, it's positive then negative. That is the normal instrument. Okay, and then you're going to have some sort of ionizing beam, some sort of way of ionizing these things. Okay, the most common is the electron collector. And so it's going to be an electron beam with an electron collector. And you literally just shoot a beam of electrons. And then your samples come through and they get electrons put on. And this causes them to ionize, often causes them to break apart because they're not stable anymore. They have an extra electron. And so it usually serves dual purposes. There are other methodologies to this. For example, you can have inductively coupled plasma. That's called ICP-MS. Those instruments are several $100,000 a piece because you need incredibly powerful vacuums. Okay, but those actually use a very, very flash. Plasma is matter that the electrons have been stripped and are moving around it. Okay, and so I don't know if you knew that, but that's what it is. And so it's another way you can put electrons on things and you can make them ionized. Okay, this is very important because you need these to have a charge. Okay, so you charge your sample, all the individual molecules and fragments of your sample as many as you can. Once they're charged, well, if they have a charge on them, then what's going to happen here? Well, this positive is going to pull any negatives this way, isn't it? Well, if it pulls the negatives this way, it's going to hit the plate and it's going to get collected by the vacuum and they're gone. Okay, and any positive ions are going to get pushed by this, right? Pulled by this one. And you'll have a little hole that's right in front of where the sample is. And so the majority of those ions are going to get pulled through that hole and they're going to be accelerated. And you're going to move them pretty fast, actually. Okay? They get moving pretty fast to us, 60 mile per hour, 80 mile per hour is fast. They're going to be a lot faster than that. Okay, they're going to be like speeds of sound sort of fast. Okay. So they're going to be zipping through this vacuum here. And what you're going to do then is you're going to have this magnetic field, okay? And what you're going to do is this is an electromagnet. You're going to slowly dial that to very little magnetic field to higher magnetic fields. So what's going to happen is depending on the mass of that, right? So if you have a weak magnetic field, and it has a lot of mass, relatively little charge. It's just going to zip and hit the side here, isn't it? It's going to overshoot is what it's called. Undershoot, undercurve, okay? And it's going to hit the side. You're going to hit this over here. It's a plate that only has a little hole through it again. And you're going to get sucked off through the vacuum. and that one's gone. Okay? Anything that has too light of a mass is going to get pulled too much, right? And it's going to hit the plate and it's gone. Okay? So you're going to end up selecting for a specific mass to charge ratio. Okay? That has the correct mass to charge ratio. And only those particles will go through. And so what you can do is as the samples are coming along, you can just dial up that magnetic field, and it's slowly going to select for different masses, isn't it? To charge ratios. Then over here, you're going to have some sort of detector. These detectors are typically measure magnetic field differences, but you can do all sorts of detectors. You can literally do it where it has like little pockets for atoms to get lost in, and it can detect the collisions of those atoms in it. That's actually how the instruments that we have work, and you can do those in air, and they don't have an actual MS, this magnetic field structure. So you can do this in a lot of different ways for the detector. That's why we just call it detector and call it good, okay? It's very similar to a Geiger counter usually, if you were looking at one of these. It's quite sensitive, actually. It can usually detect very few particles going by. So this is what we're actually going to plot out. So what we do is, again, I've simplified this. I'm going to call this computer magic and wave my hand, okay? Is everybody all right with that? Okay. In the old instruments, this was literally a amount of electricity that came per the time, and then you'd have a like calculation you would do to convert that time, okay, or voltage down here, right? But so the computer is going to convert this voltage here to an M to Z ratio, right? And then this is going to be relative abundance, and it's going to be the response of this detector. How much did that respond? Okay. And you'll get very, very sharp lines here usually for modern day instruments, right? But they look very sharp. If you start zooming in enough, most MSs, this width here, is going to be what's called the resolution of it, or it's going to be the essentially uncertain. Okay. So if you have an MS instrument that is working to the order of like it can measure within 0.001 AMU, then this is going to be very, very good resolution. And these will basically be just sharp lines. Okay? Amazing. Because that's going to be like electron measurements, right? That is totally unrealistic to actually get. They do make things that are kind of like MSs that do that, but they're not this simple. But you can actually get ones like quad ones that measure down into the fractions of an AMU. And these lines are very sharp then. If you get a low quality instrument, these lines will be broader. Okay? And they'll have some width to them. Okay. Does that make sense for everybody? Note what I kept saying MZ and mass to charge ratio is MZ. Okay? And it's very important that you understand this distinction. So if you have a 2+ charge on something, it would half the mass response, right? So you could be twice as much mass and still come through this at the same place, wouldn't you? Okay? Is that making sense? Okay. Okay. So let's talk a bit about the vaporization. So you're going to take a very small sample. It's typically going to be less than or equal to 1 microliter. Microliter, does everybody know microliter sizes? Okay, cool. That's going to go into the spectrometer. This will be immediately vaporized. It's very important to get this to vaporize extremely fast. It's one of the reasons you want to use such a small amount. And one of the benefits of this is it is a destructive technique. So you cannot recover your sample at the end. But it's oftentimes still used in art and stuff because you can take extremely small samples. Anybody ever seen a painting without its frame on it? Like an old museum piece? So what you'll see is that the really famous paintings, on the backside of them, they actually have these little dots everywhere. And it's every time they've needed to test it to see if it's the authentic painting, they're taking small little samples. Yeah. And you can take extremely tiny samples here because 1 microliter is nothing, right? It's very tiny. Once you vaporize those gaseous molecules are going to drift through a beam of fast-moving electrons. That was the ionizer right here that I was referring to. So this right here is your sample that's in the gaseous state. You're going to ionize this, so you'll have this beam of electrons. Now remember, because it's a beam of electrons, right? Electrons repel electrons. And so what you're going to end up doing is knocking electrons off. Okay? And so you typically are going to knock electrons off. This is going to give you an ionization. This is a super unstable way to ionize things, right? Because you have just made a free radical non-paired electron and made it negative, right? So you have made something incredibly unstable. This is called M+. And so even though these are moving very fast for our, normal speeds, I mean, compared to like electrons being shot at in nuclear chemistry, these are not moving fast at all. These are pretty slow. Compared to us, these are moving fast. What's going to happen is it's still going to have time to do some fragmentation. Okay, it's not going to have time to react because these are gas. If you weren't a gas, you could react, but you're a gas, so they're pretty far apart. The likelihood that they're actually going to end up any significant amount of reaction isn't going to happen. It still can happen, just not much. Okay, it's not going to have time. And so this right here is the fragmentation. These are going to be labeled with F's for fragment. This right here is the original, okay, and M for essentially mass of the original. And this right here is going to be your different fragments. So FG1, fragment 1, FG2 would be fragment 2 of this fragmentation pattern, okay? And you'll have different patterns depending on which is the order stability, right? So like, yeah, a tertiary carbocation is more stable, isn't it? But that doesn't mean a secondary carbocation can't be made a little bit, right? So you can get a little bit of that. Okay, and you'll have these different fragments. Now, when you look at these fragments, though, these neutral fragments, are they going to bend with that magnetic field? Do neutral things get moved by a magnet? You take a magnet on your desk, does it stick to the desk? No, it has to get something that has a charge to it, right? And so only this one is actually going to reach the end on any conditions. These other ones, unless you turn the magnetic field off, they're never reaching the end, right? Even if you turn it off, they're still going to hit the wall. So you're never seeing those ones, okay? It's only the ones with the charge that you see. Remember, it's M sub Z. If you have no charge, that Z is 0 and doesn't exist, right? We can't have that. So, again, you knock those electrons off of that gassy species. This is going to get us a positive charge. This M dot with a plus here, this is going to be called the electron impact ionization. And this is going to be the molecular ion, which is that M dot plus. And it's always in the gas phase because we're in the gas phase. Okay. Now, the charged species, like the M dot plus gas, can be guided into a detector through a magnetic field that will bend the ion's path. This will require one of your largest magnetic fields you would need because it's going to be one of your larger masses. Okay. The extent that a given ion's path is going to be bent is going to depend on the strength of the magnetic field that you apply, and so this will give you your mass to charge ratio of that particle based on the voltage you had to put into that magnetic field. Okay. The detector itself is going to be designed to keep track of the number of charged species that collide with it. Some of them actually literally you collide with like a little thin membrane of metal and it changes the charge, right? Kind of like a reverse speaker. So it can literally be colliding into it, then you suck off the ions, get rid of them with the vacuum. Yeah. But there's a variety of different ways these work. This is, again, very broad. Okay. This is going to be called relative abundance of the ion, is how much of it there is, and this is going to be that one right here. Now, keep in mind, because we're doing this, you may not actually have this standardized to the point where you can tell the exact amounts that are hitting here. Okay? Oftentimes you will not. This is quite variable because electricity itself is somewhat variable. Okay? Does everybody know what, like, outlets, the language for outlets of power? Like when you plug in the outlet? So what voltage is the outlets that you're plugging into? It's called 120 nominal. Oftentimes people will write like 115. Okay? And what it actually is it's a voltage that's usually between 115 and 125. Okay? If it's experiencing spikes, it can actually experience them out to 110 to 130. And so it's called 120 nominal usually, meaning around 120. Okay? And so whenever you have something hooked up to it, actually, you have to do a lot of work to keep your voltage even remotely consistent. Okay, it's actually quite difficult to do. It takes a lot of work. Okay, so the x-axis and mass spectrum can usually be interpreted as the mass of each of the ions that are detected, because most of these ions are just going to have a +1 charge, right? And so most of these are just going to directly be the mass down there, right? The m dot plus peak of the mass spectrum is taken to be the compound's molecular mass. It's usually the top one or the second to the top one. Okay, basically it's usually the top one that has the largest concentration. Right? There are a few edge cases where this could not be true, but overall this would be what you'd want to go with. Okay. Notice that it is not actually the top one in this case. Why would it not be the top one? Do all atoms of a given element have the same mass? No, there are isotopes. Yeah. And so you will see the isotopes as well in their isotopic ratios, right? And so, for example, this is almost certainly carbon-13. Okay? +1, right? So carbon-12s, carbon-13s. If you were sensitive enough and had enough of a height here, you would see the double carbon-13s, and you'd see other stuff too that's in lower ratios. But carbon-13 is already only 1% of your sample, and so, well, a little over 1%. So 2 carbon-13s is like 1/10,000, right? So again, that's your M plus right there. Okay, and that would be like your overall mass for your sample. This one's what's referred to as the base peak. It's what that relative abundance is actually set from. So this is the what out of 100 is. Okay, it's the 100%. It's the largest one. It's the most predominant fragmentation. Okay, it's the one you get the most of. So let's talk about the nitrogen rule, okay? So you may have noticed that whenever we are doing charged compounds and they fragmented, that we got different patterns from those that started showing up, right? We were talking about like what holds charges, what stabilizes charges, all that stuff, right? And so compounds that contain an odd number of nitrogen atoms are going to typically have an odd molecular mass, okay? This is because if you look at the nitrogen there, it's going to typically give you odd masses due to the hydrogen bonding. It bonding to things. Remember, it only does the 3 bonds, right? Typically. And so this is actually one of the fairly edge cases where you'd actually get an odd mass. Okay? I mean, they're not that uncommon. Nitrogen's not uncommon, but Now, a compound that contains an even number of nitrogen atoms or no nitrogen atoms at all is going to typically have an even molecular mass. Because, again, if you have 2 3s, it's going to give you a 6, right? Okay. And so, NH3, as an example, is going to have a single nitrogen atom. Its mass is actually 17. If you were to look at ethane and hydrazine, hydrazine has the two nitrogens bonded together. They'll contain 2 and 0 nitrogen atoms, and they'll be 30 and 32. And so you see they're evens. Okay. So if you see something with an odd mass, the likelihood is it is nitrogen, right? It's very, very likely nitrogen. So this is the fragmentation pathways that you would see for these various different compounds. So this right here would be your M plus right here, where it just has charge, okay? And so it's 86. This is actually this previous one right here, right? And so over here, we have our fragmentations, okay? And so this red line is where you'd actually get your fragmentation. You'll get this positive ion, which has now 1 less carbon, right? And then you get your other fragment, which is not charged, so you don't see it, okay? And so you see we have 1 carbon coming off, 2 carbons coming off, and we have 3 carbons coming off. Okay? And that gives us these different charged ones, which are 71, 57, and 43. If you look up here, you'll see there's a 71, 57, and a 43, isn't there? See those? Those are the different fragments we're looking at. Okay. So let's try this, applying this part that we've learned so far. So using this mass spectrum of the ethylbenzene here, identify the M plus peak and the base peak. What would be the formula of the ion that's responsible for that base peak? Okay. So the first thing is, which one is the M plus peak? So you're going to want to take your papers, discuss it among yourselves. Very much. That's always great. And try to figure out what those 3 things are. The base peak and the M plus peak are the really, really easy ones to do. The other one's a little bit more challenging. You got to kind of draw things out. The other 2 are definitional. Talk to each other, argue it out. God, no, I think it's this. Don't forget to commit to an answer, because otherwise you'll never know if you knew it or not. You'll convince yourselves. Yeah, I don't have to study that.
Did that sound right?
I didn't. Yeah, so your base peak is this one right here, and you basically just have to subtract off. Yep, you just take off CH3 and then CH2s. Yep. For that mass. So the difference in these masses. Yep, you got it. Yeah, you'll get a CH3 and then CH2 jumps. Okay, folks. So let's go ahead and move forward. So first off, the first thing you want to do is the M plus peak is which one? The one at the highest point right here, right? Yep. So this is that M plus peak. Okay. And that's essentially the mass of your entire compound, right? Or at least the predominant isotope for the entire compound. All right. And so the next one right here is going to be the what? Base peak, yeah. It's always 100%, right? So whatever is your 100%, it's your base peak. Okay, because that's the one with the largest abundance, isn't it? Remember, this is in relative abundance. Okay. And so what you're going to notice here is, first off, you kind of have to look at your structure since you've been given it. And you have a little bit extra information that makes this a little easier for you. But typically, with speaking, you're going to lose essentially functional groups, right? So in this case, we just have a benzene and an alkane, don't we? Or an alkyl, I should say. And so the benzene is going to be left untouched for this first part, isn't it? Because it's the most stable. And then you're going to lose essentially a methyl. And then the next one you would lose is an ethylene, right? CH2. Okay. And so the spaces between these things, they're going to be very even on these alkanes because they're always going to be losing a CH3, CH2, CH2, down, right? And in this case, you're going to pretty rapidly end up hitting a point that's stabilized, right, by that benzene ring, which is going to have that resonance stabilization RJ. Okay? And so one of the things you have to keep in mind when you're doing this is you have to look at your amount here. So if we were to look at that M plus peak, we would see that it's like 106, right? See, it's one line up. Okay. And so that's 105, that's 106 then. Okay. And so that's going to be your base peak. It's an even number. So you know that it doesn't have probably a nitrogen, right? Or if it had nitrogen, it had two. Okay. And so then you look at your next peak, which is going to be that tallest peak, right? Which is going to be your base peak. And you're going to look, and it's about 91 right here. That'll be your 90, right? And then 91. And so you're going to go through, and well, what would be a difference of 15? What would have a mass of 15? That's the difference between these, right? Yeah. So if we take off a carbon, that's 12, right? Yeah, 3 hydrogens, that's 15. You got it. And so taking off that methyl, that'd be your 15 in mass, wouldn't it? Okay. Did that make sense? Yeah, conceptually, this is actually kind of like, yeah, very simple math and makes a lot of sense. We'll add some layers on this, so I want to firm up your base as best as possible. But yeah, it's nothing that you couldn't have already figured out by yourself. Okay. Okay. Did that make sense for everybody? Okay. Yeah, I want to make sure that we have a nice firm base going into this. And overall, I want to make sure that you have a nice firm base going into characterization. Because interestingly enough, in many ways, it's one of the most useful knowledge bases, even for medical professionals. Because characterization is something that you'll actually see all throughout your careers. And if you don't know anything about the methods, you're going to get fooled. If you know something about the methods, then you don't get sold a Pyroluck. It will help, right? It does help. The number of medical professionals and dental professionals that are coming up with new techniques and stuff that have come and consulted with me over the years is drastic, and it's because they don't know almost anything about spectroscopy. So, again, the M plus peak of hexane, this is going to appear at 86 here. Notice again, there is that small peak. I made you kind of come up with it. This is called the M plus 1, right? It's the mass plus 1 more. Okay? And that's that small peak on the side there. Very, very tiny. And so that is, of course, your isotopes. Yeah. Yes. Because it's a neutron. You'll always get a plus 1. But you'll also get another one that's can be higher. Yeah. Yes. Yeah. There are examples that are plus more. These are the isotopic ratios. They're not carbon. Yeah. Huh? Yeah. Okay. And so you always will get a plus 1. That will always exist. Okay? However, keep in mind, this is like a 1.6%. Okay? And so if you have other peaks that are much, much larger, you can get it so small that maybe you can't see it, okay? If your response here was already too small, then you may not be able to see this, right? It is very easy to miss, because it is like 6% of that, right? Okay. And everybody understands that is your isotopic ratio, right? And that's the C13. Okay? Okay. Now you have other isotopes, okay? And so the abundance of C13 is actually 1.1% of carbon atoms is C13. You don't need to know you need to know the carbon exact ratio. Yeah, 1.1. 1.1. But typically you're not going to need the other ratios. You just need to ballpark it and know that, like, for example, chlorine and bromine, yeah, they're typically +2, right? See the chlorine and bromine here. Okay. This is actually why, by the way, they have that. Yeah, if you look on the periodic table, these are weighted ratios. So there are the weights that you see right here, right? Times, exactly. And so they're the weights right here times that abundance, then you add them together, just like your grades, right? And so what happens there is you get the 0.4, and yeah. Notice it's not really that close to either of these, though. Yeah. Because they're pretty even ratios for bromine and chlorine. So right here, when you see like a +2 and M+2, that's going to be a pretty big peak because you're seeing like 24% abundance, right? And so you're going to see a 24% abundance one. That's about 1/4, right? That's typically going to be a chlorine. If you see a +2 and it's about half and half, that's typically going to be a bromine, isn't it? Okay. And then sulfur, silicon, you can see that these show up with some pretty interesting isotopic ratios. Typically, sulfur can be like a +2, but it's only a 4% again. So you're going to see a small 4%, right? Okay. And then silicon is actually one of the more interesting ones because you can get kind of a... yeah. But again, very tiny ones, right? So you may not be able to see them easily, okay? But these are relatively uncommon again. Most structures you're going to look at are going to be combinations of carbon, hydrogen, nitrogen, oxygen, right? Sometimes you'll get chlorine and bromine. Those aren't that uncommon in chemistry. Silicon, though, sulfur, these are much more uncommon, okay? Unless you're specifically doing something. Notice that you would actually be able to see if you got a... good enough lower limit response on your instrument, you will see these other isotopes, okay? And so, for example, you could actually see the hydrogen isotope deuterium if you get a good enough response, but it's very tiny, okay? Nitrogen is more likely if you have the nitrogen. It's, again, going to be a +1, but it's still much, much smaller than that 1%, right? You're talking about another third off of that. And so think of that as another third off that. How small that would be, right? Yeah, you can barely see it. Okay. And of course, like oxygen, you basically don't see usually. Okay. You can see them if you get a really great instrument. Okay, so the M+1 peak for small and medium-sized organic molecules, that M+1 is going to oftentimes be identified as the 2 peaks with the highest mass right here in that spectrum. One of the things I need to make sure that you understand is that this is like 1.1% of carbon atoms, right? If you have 1,000 carbon atoms, then you're seeing lots of C13s in there, aren't you? Okay? So it goes up the likelihood of seeing this depending on the number of atoms you have, right? Okay. Per atom. So this is an M+2 peak right here. And so this would be a 3-to-1 ratio right here between the M+ and the M+2 peak. If it's a 3-to-1 ratio, then that's likely chlorine, isn't it? Because that would be a 24%. This right here is bromine. It's about 1-to-1. It's not quite a 1-to-1. They'll be a little bit uneven. Okay. But you'll always get very near 1-to-1. Okay. And that's a bromine +2. M +2. So this is an actual spectra of a bromine on here off a benzene ring. And here you have your M and M +2. And you see how they're just a little bit different, okay? Yeah. So very, very close to the same heights. You have a +2 to the M right there. Can everybody recognize that okay? Nobody's having trouble. Okay. So right here we have one that's going to have more fragmentation happening. And so here we see these M and M +2, right? Right there. But notice what happens when we still have the bromine in our fragment. What do we always see? A +2, right? We're always getting a +2 with about the same height ratio, right? And so that is always telling us, hey, I have the bromine still. Okay? If the bromine comes off, what's going to happen? We won't get the +2 anymore, will we? We're just going to get that +1s and small little things, right? We're not going to get that +2 anymore. That's about the same height. Okay? Because that doesn't have bromine in it. Bromine has fragmented off, and it's a neutral fragment in most of those cases. Okay. And so does the compound that produced the spectrum shown here contain chlorine or bromine? That was immediate commitment. That was good. Yes. You are absolutely correct, and I am very glad that hopefully everybody else also had that immediate visceral response, and it wasn't just... But
So now I'll never forget it. You're not.
Fantastic. Yeah. Okay. So, it's the M +2, right? And you're looking at the M +2, and in the case that we just looked at, this is about a 1-to-3 ratio, right? So it's 24-ish%. And so that is, of course, the chlorine, bromine would have had equal. Yeah.
That's our question.
No, you would be expected to know that chlorine is the 1-to-3, bromine is the 1-to-1. And that carbon is going to be tiny 1. Okay, so let's talk a little bit more about this, because you can actually use this ratio right here because it's math, right? It's going to be predictable. So if you know relative isotopic abundances, which we do, okay, it's something that's tabularized and we've explored extensively across this planet. By the way, if you go to a different part of the solar system, those isotopic abundances will change. Okay, just as a reference. And in fact, the carbon in the atmosphere and now on the surface of the planet, the relative isotopic abundances have changed on the planet, Earth. An interesting little factoid. Because, do you guys know what dead carbon is? It is from dead things. So, in the atmosphere, cosmic particles zip in and they fragment different molecules in the atmosphere. Mostly they join up with nitrogen. Nitrogen falls apart. It gives you carbon-14. Anybody ever heard of carbon-14 dating? Yes. And so that eventually decays down to your carbon-12s. And so we are actually modifying the isotopic abundance of carbon by burning fossil fuels, putting in carbon that has decayed mostly. And so that doesn't have the same ratio. Okay. It's not really affecting the carbon-13 ratio that much, But the carbon-14 to carbon ratio has changed a lot, actually, over the last 30 years. Yeah. So, interesting little factoid. Okay, now, again, depending on that number of carbons on your structure, right, you're going to have a bit different of a height of your M plus 1 versus your M plus. Okay? That's going to give you a different relative height here. Because remember, you have a 1.1% chance of each carbon being carbon-13, right? So if you have 100 carbons, 50% of your molecules are going to have a carbon-13 in them, aren't they? Okay? That's how probability. If you flip a coin 100 times, right, you're going to get half heads, half tails, right? Yeah. It's a 1 in 100 ratio. So if you have 100 of them, one is likely to be a carbon-13. No, it's not 50-50. Again, that's why I said 100 carbons. No, it's 50% likelihood of finding a carbon-13. Yes. Yes. You don't get assured 100% chance of getting a carbon-13 when you do it 100 times. That's the majority, which is the 50% mark, is what you're doing. Anyways, so what you need to do here is you need to remember that we're actually going to give you a little formula here. This would be a good thing to put on your sheets, by the way, because even I don't remember this formula. I have when I don't use it that often, and so like first time I use it, which is this, I typically have to remind myself what the hell the formula was. But this is the formula right here. So your number of carbon atoms in your molecule is going to be approximately, everybody knows that wavy? Okay, approximately. This is not going to give you the exact number. You're going to get fractions. You're going to get slight mismeasurements. You're going to get, it's not going to be perfect. Okay? But approximately going to be the intensity of the M plus 1 divided by the intensity of the M. Then you times that by 100%. Divided by 1.1. Okay? Now, this is given to you like this instead of simplifying this number here, so that you could replace this number here with whatever isotope you want for anything you want to do it with, right? And then it would be the number of nitrogens, it would be the number of bromines, it would be the number of whatever. Okay? Yeah. But this right here, again, you plug in your intensities here, and then remember that these are going to be flipped. Okay? So this is out of 100% for the M plus 1 abundance, whatever that isotope is. Okay. So let's try it out. Let's see if you can plot. Estimate the number of carbon atoms in the compound that's produced the following mass spectrum. You're going to want to measure as sort of best you can based off these lines here. Kind of going, this is about a third of this, right? This is zoomed in enough, you'll get an answer that you can round to the correct one. Often when you're doing this, you're going to be using spectra that was republished, and you won't have the numbers. You'll just have to measure them best you can. The easiest way to do that is, like, this is a third of this. This is the 100 right here, right? Again, feel free to talk to each other. By the way, I will need your helps next chapter because I know way too much about the material. I can very easily just like go on forever. Okay? No. You actually really, really do want to get my expertise and learn as much as you can from me on that. because you will not get somebody like me for less than $800 an hour
Okay.
in the future. Yes, and for the MCAT, if you're taking the MCAT and any other standardized exams. It's one of the most popular questions on like PCAT, MCAT, any organic exam of any type. Is the like identify the spectra, where would this compound show up, that sort of thing. So the baseline is always going to be the 100%. This is the same. They're the same. Yeah, it doesn't matter here what the baseline's position is in this way. It's just the one that's the most common to hit the. Oh, okay. Okay. Okay, so what we're going to do here is if we look at this, it's again about a third of 20%, right? So about a third of 20% is something close to 7%, right? Okay. And so we plug in 7% out of 100%, which is the 100%. And then this is going to be times 100%, which is over the abundance of carbon-13, right? Because we're doing carbon-13 here, because of the plus 1. And so this is going to give us a 6.4. Notice again, this is a weird fraction, right? But you can round that. If you round that, that's going to be 6. Okay? And so you'd have approximately 6 carbons in this entire structure. In this case here, this was this height. This is 20 here. See, this is the 20 I was referring to. Yeah, so 1/3 of 20 is going to be approximately 7. Yeah. And then this one's 100. Oh, okay. What do you mean 5 blocks? Anyways.
I was doing the same.
Oh, yeah. Yeah, you can do that too. Yeah. Okay. So we got the 6 carbons. So whenever you're doing this structure, you'd want to go, yeah, it probably has 6 carbons in this. Okay. Interestingly enough, you can apply this to many, many different things as long as you have the relative abundance of them. For example, you can do it with bromines, of course. You can do it with anything you have the relative abundance of. So like, how many bromines do I have on this? You don't normally need to do how many bromines and chlorines I have. It's unusual to have more than one. But if you ever need to, there you go. So let's talk about some strategies for success before we get into actually trying to like solve spectra for these things. We're going to assign the M plus peak. You always want to get the M plus peak first because that's going to give you your total MZ value for that compound, right? So if the M plus peak is not already given, try to assign it as follows. At the high mass end of the spectrum, you're going to look for 2 major peaks. They're going to be separated by 2 units of MZ values if you have a bromine or chlorine, right? It'll be +1 if you have only a carbon. Look for the +2 first because you want to eliminate that first. Okay? It's always, this is science, right? So we try to eliminate things until we find the truth. Okay? That's how you systematically always solve problems, right? You don't try to build up things because then you can false narratives and it causes you issues, right? Okay. So if you locate that M plus 2 pattern, then the lower of the 2 MZ values, that's going to be your M plus peak. The higher one is going to be that M plus 2 peak, right? If you don't have a +2 peak and that's not apparent, then you're going to find your 2 highest mass peaks. whose difference is different by 1. Okay? And so these are going to be the ones that'll be your M plus and your M plus 1. Okay? Okay. So once you have those values, well, you can actually use those isotopic ratios to figure out the number of carbons that's going to be in your compound. This gives you a really great place to start with, right? Because if you know the total number of carbons, mathematically, your possibilities are very limited, okay, by that total number of carbons, right? And so you can really, really limit the number of things you have to consider, okay? Which is why it's step 2. So you're going to record the number of carbon atoms. The number of carbon atoms is not given. You need to estimate it. And you're going to do that by plugging in the M plus and the M plus 1. Sometimes the number of carbons is just going to be given to you. Okay? It's for a variety of reasons. If you were doing this in a lab setting, you could know the number of carbons by the fact that you only had a structure that you didn't add any more carbons to, right? Unless it like doubles the mass or something, you know, that's how many carbons you have, right? You could also know this by the fact that I give you a problem where I just tell you the number of carbons, right? Okay. I typically do that when the spectra would be very difficult to read the plus 1 peak. Okay. Now, number 3 is going to be determining if the molecule contains any heteroatoms. Does it have things that are not carbon and hydrogen? Things like bromine, chlorine, nitrogen. Okay. The nitrogen's the easiest one to deal with first. And so we do that as the first part of this. We're going to do the nitrogen rule. Is it odd? And so if it's odd, does it suggest that it's nitrogens? The total mass. Yeah. If the total mass is odd, that suggests you might have a nitrogen atom. Okay. Again, it is possible to get an odd compound that is not nitrogen. However, nitrogen is the leading cause of that. It is far, far more likely to be nitrogen. Okay? Unless you have some other piece of information that tells you. I would look for nitrogen. If the M plus 2 peak is present, do the relative intensities of the M plus and M plus 2 suggest the presence of bromine or chlorine? Do you have the 1-to-3 ratio or 1-to-1 ratio, right? Okay. Notice these are not mutually exclusive. You can have both. So you can have an odd with a nitrogen and have a chlorine or bromine on. Okay? It is possible to have both options. It is also possible to have both a chlorine and bromine. Okay? In which case you'd actually have like a complex ratios. But I'm typically not going to give you, I'm not going to give you problems like that. It's just, that would be a higher level of expertise than you need for the class. Now, determine whether hydrogen atoms can account for the remaining mass. So if you can account for that remaining mass with hydrogen atoms, then you have a complete molecular formula that could be feasible. If the number of hydrogen atoms is unreasonably high, then what you need to do is, I'm sorry, I skipped one. You need to compute the remaining mass. So what you need to do is you need to subtract the masses of C12 atoms you determine in step 2 from the mass of the heteroatoms you determine in step 3 from that molecular mass. And then you need to determine if the hydrogen atoms can make up that remaining mass. Remember when we were doing the previous problem and we're like, this is CH3, right? And so we went down 12, right? And then we went, okay, does it go 1 more, 2 more, or 3 more? Okay? If it goes 1, 2, or 3 more, then that's a CH1, CH2, CH3, right? Okay. If it's CH4, is that likely? No, that wouldn't have been attached, right? That would have been a separate methane. So that's probably not a carbon and hydrogens, right? It's probably something else. It could be a heteroatom. Okay. How about mass? So if we're at 16, if we're at 17, if we're more than that, it's not a CH3, is it? Okay. Now it only becomes another carbon fragment once we start getting into like the 24 plus hydrogens, right? and then we can start making up that mass. Does that make sense? So it's going to be multiples of carbons and hydrogens attached to them. Okay? There you go, what I'll look for. So if that complete molecular formula would be feasible based on those carbon-hydrogen patterns, then you know it's carbon-hydrogen atoms, and you're good. If the number of hydrogen atoms is unreasonably high, then you have to consider adding another non-hydrogen atom. You might have to do a C2, right? 2 carbons. You might have to do an oxygen. What's the mass of oxygen again? 16. And so that would be your normal 16 if you have an oxygen. Fluorine, that would be your next one up, right? And so that would be where you'd start seeing those heteroatoms and they'd show up. Okay. Okay. This is the first unknown that we're going to talk about, and we'll do this next time. So I will have this, look at it really good, burn it in your minds. I want you to dream about this. You'll have nightmares that you don't understand it, or you do understand it. One or two. I'll have to determine which of those dreams and nightmares. But you all have a wonderful day. I will see you next time. And what's happening next time again? The exams. Yes. Please come prepared.